In the previous video, we have discussed about the critical section. So just a review, each process has a segment of code called the critical section, in which in this section, the process may be accessing and updating a data that is shared with at least one other na process. So in order for us to avoid race conditions, the execution of critical sections must be mutually exclusive, or that when one process is executing in its critical section, no other process is allowed to execute in its critical section. So that is, no two processes are executing in their critical sections at the same time, or at most one process can be seen at the critical section at any time. Okay, so we already discussed this. So we have this pseudocode for a specific the process and its critical section, wherein that part is where the code is executing a shared or maybe accessing a shared resource. Okay, so this is the entry section wherein it controls the entry to the critical section and obtains a lock on the necessary resources. So once this is locked, so no other process can execute on the critical section. And then once this is done, then we go to the exit section and the lock is eliminated, or the lock of the resources is eliminated. Now our problem is to design a protocol that the process can use to synchronize their activity as to cooperatively share data. Okay, so implementing this must satisfy some requirements. So first is there's the mutual exclusion. So no two process may be simultaneously inside their critical sections. And for the progress, then no process running outside its critical na region may block other na processes. And for bounded na waiting, then there exists a bound or a limit on the number of times that the process are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. So no process should have to wait forever in order to enter its critical region, or no deadlock or starvation. Okay, so the critical section problem is to design a protocol with which processes can use to cooperate and ensure mutual exclusion. Now the problem would be, how can we design those entry and exit sections so we can satisfy the previous requirements mentioned, the mutual exclusion, the progress, and the bounded no waiting. Okay, so we have the Peterson solution. So in this solution or algorithm, so in this case, there are processes that are sharing these two variables, the turn and the Boolean flag. Okay, so this code will keep on running while it is true. So we, as mentioned, this is, let's say, a pseudocode for one process, all right, for one process only. So it has a turn, and that turn will indicate whose turn it is to enter the critical section. And it has also a flag, and the flag array is used to indicate if a process is already ready to enter the critical section. So if we have flag of I, it implies that a certain process P sub I is ready. So notice the index here. So it can enter a critical section when a process gets its turn and the other process is not ready. So how can we further explain this part? So first is that, again, this all of this code are in this do while na loop, and this will keep on running while it is true. Okay, so now first is that process I sets its flag as true. So initially, the Boolean flags are both false for the two processes. Okay, let's say the process I is now ready to enter its critical region. So it sets its flag as true. Okay, now it's a humble na algorithm. So before it can enter or even if ready na mag-perform si I, it's a humble algorithm. So instead of like turn of setting its turn to itself, it gives way to process J. So essentially, the process I indicates that it is process J's turn. Okay? So the turn is set into the other process, which is J. So you can think of it like, let's say you are queuing in in an ATM machine. Okay, and there is a senior citizen at the back of you. So instead of you are ready to use the ATM machine, but then you let the senior citizen at the back of you to have its turn first. Okay, so yeah, you set turn into J, and this is the highlight actually of the Peterson's solution. So the while loop will has a two na conditions here, the flag of J and the turn of J. Kasi nga, it is a humble algorithm. So we have set we have set turn into the other process, which is J. Okay, so in this case, you can see here that we have a while loop with two na conditions, that the flag of J and the turn of J, right? So meaning this will keep on running, this will keep on executing if it is still the flag of J and it is still the turn of J, right? So in this case, um, process I, will not be able to enter its critical section while this while loop is true, right? So the while loop will continue looping if the flag of J is true and it is still the turn of J. Okay, so it means that process J is in its critical na section or region, and therefore the process I cannot enter its critical na section while this is continue to loop. So once it becomes false, meaning magiging false lang siya if this is either this will become false or this will become turn equals I. Okay, and after, let's say, this becomes false na, then the process I can now enter its critical section. So after some point that the process I is done with its critical na section, then it will set its flag into false, right? Set its flag into false, and it execute its remainder na section. Okay? Now, how can we prove that this algorithm is correct? So earlier we had some conditions or requirements so that we can meet or we can solve the critical section of problem. So ideally, the mutual exclusion should be preserved and the progress requirement is satisfied and the bounded no waiting requirement is met. So let us check if this Peterson algorithm will satisfy all these requirements. Okay, so initially again, we have we have a flag array which contains the boolean for our two processes 0 and 1, let's say. So for P0, that is its flag of 0, and then flag of 1 is for P1. And we also have a turn na variable that indicates if it is its turn to be in the critical na section. Okay? So yung flag naman indicates if ready na siya mag-enter sa critical section. Okay. So again, we have this two pseudocodes. So for this first na pseudocode, this is for the process 0. Okay, so process 0 is ready to enter its critical section, so it sets its flag into true. But then it's a humble na algorithm, so it sets the turn into 1. So ibibigay niya yung turn for process 1. Okay? And while flag is 1, is equal to true, or let's say while flag is 1 is equal to true and turn is 1, this will keep on looping and the flag of 0 will not be able to enter its critical section. Okay? And let's say at some point now this becomes a false, then this will be able to run its critical section. And after it's done, then it can set its flag as 0 as false. And pag naging false na ito, then this will result into a false, right? So this will become false and this will become true. So this will be false and the process 1 can enter its critical section. So I have already discussed this part earlier. So let us discuss for flag 1. So for flag 1 naman, similarly, it sets its flag as true also. And since this is also humble, so it sets the turn for 0 for this process. Okay? And while the flag is 0 and turn is 0, meaning this process 0 is running in its critical is in its critical na section. So while this is true and this is true, then this process 1 cannot enter its critical na section. Okay, and let's say for some time na this becomes false, then this will be able to run its critical na section. And then after some time na mag-exit na siya, then it sets its flag into false. So pag naging false na ito, then pwede na ulit mag-run. Magiging false na din to siya. And then pwede na ulit mag-run si process 0. Okay, so they are taking turns. So let's say if this is false and this is true, then it enters and sets its flag to false after done with the critical section, executes the remainder. So since it becomes false, and let's say naging true ito, then it can enter its critical section, false, and so on and so forth. Okay, so they can go back and forth. So now we wanted to prove if this algorithm is correct. So is the mutual exclusion preserved? Okay, so in here, the process 0 can only enter this critical section if the flag of 1 is set into false or turn is 0. Kasi this will only return true if flag 1 is equal to true and turn is equal to 1, or both of these are true. So if just one of this becomes false, then eventually this while loop will stop. Kasi nga and siya, and it requires that both of these will be true. Okay? So for the other na process, P1 can only enter its critical section if this flag of 0 is true or is false pala, sorry, or the turn is equal to 1. Okay? So meaning turn na ni 1. Or turn ni itong process. Okay? So the value of the turn, as you can see, cannot be both 0 and 1 or cannot be 0 and 1 at the same time. So it cannot happen that this will be 0 and this will also be 0, or that this will be 1 and this will be 1. So it cannot be 0 and 1 at the same time. So two processes cannot be in critical section at the same time as well. So since two processes cannot be in critical section at the same time, then we can say that the mutual exclusion is preserved. Now, is the progress requirement also satisfied? So assuming that this process 1 wants to enter its critical na section. Okay, so if PO is not ready, let's say naging false na siya, then the flag of 0 is false, and so then the P1 can enter. P1 can enter. Okay, and also suppose that P1 wants to enter its CS. So P1, and if both are ready, let's say both of this are set into true, flag of 0 is true, and flag of 1 is true, So if turn is equal to 0, then sorry. So turn is equal to 0, then this can enter its critical section, P0, and then if turn is equal to 1, then this process can enter its critical section. So either cases, some waiting process can enter the CS. So there is, we can then say that the progress requirement is satisfied. Because again, how about for the third na requirement or condition? So the bounded na waiting requirement is met. Okay, so suppose that P1 exits its CS, so exits its critical na section. So the flag 1 is false. So then the P of 0 can enter. And if P1 exits CS and reset flag 1 is true, then and turn is equal to 0, then it overrides the P0 setting and the P0 can enter. So we have the uh, bounded waiting requirement that is met, since the P0 won't have to wait indefinitely.